1 fundamentals, 1.1 real numbers. So we're going to start out by going over number sets. I have this nice diagram for us. We start out with natural numbers, and that includes 1, 2, 3, and onward, and it's notated by n. We then have whole numbers, which is notated by W. And the only difference is it includes the natural, but it also includes 0. Up next we have integers, which encompasses the whole and the natural, as well as negatives. And it's notated by the letter Z. After integers, there are rational numbers, and this is notated by Q. It includes your integers. It also includes decimals that end or repeat, as well as fractions. It also includes square roots of perfect squares, such as the square root of 4, because we know that goes to 2. All of these are called real numbers. There are also irrational numbers. And in that we put pi, which is 3.14, but it keeps going in, it doesn't repeat. There's also the letter E. Imperfect squares, so say the square root of 5, or decimals that don't end or repeat. And then in a different category that is not in real numbers is imaginary numbers, which is I, square root of -1. So we have properties of real numbers, and these hold for multiplication and addition. So the commutative property is where you have two numbers, 1 plus 2, and you switch the order, you still get 2 plus 1. For multiplication, it would be 2 times 3. It's the same as 3 times 2. The associative property has 3 numbers. So if we have 1 plus 2 plus 3, it is the same as 1 plus 2 plus 3. For multiplication, 2 times 3 times 4 is the same as 2 times 3 times 4. And then we have, along with it, the distributive property. When you have 5 times x plus 2, when you distribute, it becomes 5x plus 10. This should all be a review for you guys. There's also a lot of properties about negatives. We know that a negative times a negative is a positive, and a positive times a negative is a negative. There's many rules of fractions. When you multiply, you can either multiply across and then look to reduce, or you can look to cross reduce and then multiply across. Here, 2 and 5 do not reduce, nor does 3 and 4. So you just multiply across, you get 8 over 15, which is not reducible. When you are dividing fractions, you have to multiply by the reciprocal. So if you have 2 times 3 divided by 4 over 5, you have to multiply by the reciprocal, so 2 over 3 times 5 over 4. If you would like to cross reduce, you can on the 2 goes to 1, the 4 goes to 2, and you get 5, 6. When adding and subtracting fractions, you must have a common denominator. So if you are adding 1/2 plus 1/3, 2 and 3 both go into 6, so you have to multiply 1/2 by 3 over 3, and 1/3 by 2 over 2. It becomes 3/6 plus 2/6, and it goes to 5 over 6. For subtracting, if you had, let's say, 1/2 minus 1/8, 2 actually goes into 8, and we only need to multiply 1/2 by 4 over 4. And we get 4 over 8 minus 1 over 8, and we get 3/8. I included proportions in the fraction section because proportion is two ratios set equal to one another, and ratios are written as fractions. So if we have 3 over 4 equals x over 8, you can either cross multiply or use what I like to call as the heart method. Where you go across and bring it down and multiply 4x. 3 times 8, set them equal, goes to 24 equals 4x, and we know x equals 6. It's possible to use LCDs to add fractions, and we're going to break them down into prime factors. So we have 36 on the left fraction, we got 120 on the right. 36 broken down into its prime factors is 2 squared times 3 squared. 120 broken down would be 2 cubed times 3 times 5. So their LCD, it is 2 cubed here times 3 squared from here times 5, and that all goes to 360. So we see that the first fraction, 5 over 36, needs to be multiplied by 10, which goes to 50 over 360. And we see the second fraction, 7 over 120, needs to be multiplied by 3, which goes to 21 over 360. And all we do now is add the top. 50 plus 21 is 71 over 360, and this is irreducible. So we are going to begin using sets and intervals. In a set, is a collection of objects, and those objects are called elements of the set. So we use a notation such as A is an element of set S, or B is not an element of set S. So perhaps we have the set A. It's labeled set A, and it contains the numbers 1, 2, 3, 4, 5. Instead of listing out 1, 2, 3, 4, 5 every time, we can use what's called set builder notation, where A contains X, where X is an integer, where 0 is less than X, which is less than 6. Does that make sense? X is greater than 0 because it's 1, and it's not including 6, it's only including 5, and it says the word integer, so we know there are no fractions included. So we could have many possible sets, such as S, which is 1, 2, 3, 4, T is 2, 3, 5, 7, and V is 9, 10, 11. A union of two sets, S union T, is just a U in the middle. It's the set that consists of all the elements in S or T, or in both. So when we write out S union T, we want every number that's in S or T, but we do not write repeats. So we get S union T to be equal to, and we use the brackets, we have 1, we got 2, 3, 4, 5, and 7. And then we close it with the brackets. An intersection, S intersect T, which is an upside down U, is a set that consists of all of the elements that are in both S and T. So we want the ones in common. So when we are looking for S intersect T, we want the number that's in S that's also in T. So we see that there's a 2 in both. So we put it in the brackets. There's a 3. And that's all they have in common. So we close it. Then we have what's called the empty set. And that's a set that contains no element whatsoever, and it's a circle with a line through it. We have already done S union T. We have done S intersect T. Now let's do S intersect V. So we want to know what they both have in common. So we go back up. So S has 1, 2, 3, 4. V doesn't have any in common with it, as it's 9, 10, 11. So how we write it, we have S intersect V equals the empty set.